rather, but we can do a direct chemical reaction there, and we can determine the amount of food, the amount of energy in a certain, in a fixed amount of food. So when you study this particular, the energy aspect of the chemical physical processes there, we have to define what we call a system and surrounding. So in this particular case, when you look at this diagram there, then this will be your system. Okay, that's the source of the energy. Okay? The surrounding would be anything outside of that. But anything outside of that, that's a fairly large scale. We don't really need to focus on the entire universe when we do the study of energy there. So the system would be an object or a collection of objects being studied. And then it's any part of the universe that is interest of us. So we're interested in how much energy is present in this fixed amount of food. So we want to, that's our system. And then the surrounding would be everything outside of the system. Well, it could be the entire universe except the system, but it could be part of the universe. Okay? And we can insulate a certain area so that there is matter or energy transfer between the system and the surroundings there. And we don't have to put the entire universe outside of the system as our surrounding there. So it can be part of the universe. Okay? So in this case, and everything else in the universe except the system, that's our surrounding. And by measuring the energy flow between the system and surrounding, we can determine the amount of energy being transferred. So an example here, if you're doing a chemical reaction, okay, now this is, if you have naphthalene, carbon 10, hydrogen 8, you burn it in the presence of oxygen. Naphthalene is a hydrocarbon. You only have carbon and hydrogen in there. When you burn it, you always get carbon dioxide and water. Now, the amount of energy released from burning naphthalene is every mole of naphthalene will give out, after a complete reaction with 12 moles of oxygen gas, you get 5,156 kilojoules of energy. So this is what we call an exothermic reaction, the term that we use to refer to a process that releases energy into the surrounding when a chemical reaction is finished. So if you look at this particular reaction here, these are the matter aspect of the chemical reaction. Two chemicals react with one another, recombining, all the atoms recombine, you end up with carbon dioxide, you end up with water. Those are the matters. There is also another component in this process, the energy component. So when you look at energy as a product, if the energy is on the product side of the chemical reaction equation, then we have an exothermic reaction. Basically, that indicates when you have these two compounds reacting, or chemicals reacting with one another, in addition to these two compounds, we also have energy being released into the surroundings. So this is an exothermic process. What happens here is that the system is giving out energy to the surrounding. So if you measure the temperature of the surrounding, you see a temperature increase. So by convention, we always try to look from the system perspective. So if you're inside the system is giving out energy to the system is losing energy. So we use a negative sign, Q representing the amount of heat being released there. Exothermic, Q is a negative number because Q to the system is releasing energy to the surrounding there. So that's a negative number there. Okay, so exothermic process, energy is transferred from the system to the surrounding. System is losing energy. So if you are looking from the system perspective, Q, the amount of energy transferred, is a negative number. On the other hand, endothermic reaction, if you have, say, a piece of marble, calcium carbonate. Now, calcium carbonate is fairly stable. Under normal condition, it will stay as calcium carbonate. However, if you heat up calcium carbonate, when you provide large enough, high enough amount of energy there, you can convert calcium carbonate into calcium oxide, carbon dioxide. So this is a chemical reaction there. Now, when you look at the chemical reaction, this is what we call an endothermic reaction. Endothermic reaction requires the participation of the energy. You have to supply a certain amount of energy in order for these two compounds to be formed. Without this heat. Without heating, calcium carbonate will stay as calcium carbonate. So if you look at the chemical reaction from both matter and energy perspective, and we can say that energy is actually one of the reactants. Now in the exothermic reaction, energy is one of the products, carbon dioxide and water plus the energy. Energy is the product on the right side of the equation. In this particular case, an endothermic reaction, energy is part of the reactant, one of the reactant in there. Without that, the chemical process is not going to happen. Okay, so in this case, energy is actually flowing into the system. You have to supply that energy. So the system, if you stand inside of the system there, and you can see the energy is increasing, so Q is a positive number. The energy for the system is increasing. Okay, so in this case, the endothermic process, energy is being transferred from the surrounding to the system. A good example here is that if you have some ice, you want to melt it, and you heat it up. You are supplying energy. Energy is getting into the system. Ice is melting into water. Okay, so that's how we define those two terms: exothermic, endothermic. Exothermic energy is coming out of the system. Endothermic energy is going into the system. So those are the terms. And how do we quantify the amount of energy? Or another question, where does this energy come from? We mentioned that when chemical bond is formed or when chemical bond is breaking bond requires energy, and then bond formation releases energy. So for a particular process, whether it's endothermic or exothermic, it all depends on the total energy required for breaking the bond versus the total energy required for the bond release for the bond formation. The difference between those two will determine whether a process is endothermic or exothermic. So the conservation of energy basically says that for the exothermic reaction or exothermic process, energy loss from the system is gained by the surrounding. So there's really no loss of energy, or you're not destroying the energy. Rather, it's being transferred from one place to another. That's what really happens there. So the surrounding, you will see an increase in temperature in the form of a thermal energy there, and when the energy is being transferred to the surrounding there, and you can actually measure that as the temperature. You will see a temperature increase there. And then for the endothermic reaction, energy gained by the system is actually the energy lost by the surrounding. So again, the conservation of energy, that's a very important concept there. Energy is being transferred from one place to the other. Yeah, it's never lost. It's always conserved. You always have the same amount of energy in any physical chemical processes. So that's something that we want you to remember. Now, of course, when we're studying energy there, we want to quantify how much energy. So when we try to quantify the amount of energy, we have to have a unit for it. And one of the 7 SI base unit, energy is measured in joule. How do we define joule? Well, it depends on what you're looking at. In physics, and when we study the energy there, joule is defined as the amount of energy needed to move a kilogram of mass by a distance of 1 meter. So 1 joule equals 1 Newton times 1 meter, or 1 kilogram times a meter squared over a second squared. So there are different definitions for 1 joule. For electrical energy, it has something to do with the amount of current in amps passing through